Hello. So in this video, we will introduce a technique in quantum field theory known as Feynman parametrization. Okay, and it involves integrals like this. Okay, and how to evaluate them. So that this integral looks daunting. It is from quantum field theory, and you arrive it when trying to obtain for the uh, loop correction. So the electron vertex when you do the Feynman diagram, and then you consider the loop at the vertex. Okay, so you obtain these corrections to the lowest order contribution of the amplitude to the Feynman diagram, and basically you get an integral that looks like this, which is it's okay if you don't understand it, but mathematically we're looking at an integral which is comprised of, in their denominator, it has like a product of factors. And the technique of Feynman parametrization is basically to combine this denominator into a single factor raised to some power, and then at the expense of introducing additional parameters upon which you integrate. Okay, so the nice thing about this is that once you were able to combine all of them in a single power, what happens is you can like shift a variable and then you complete the square and do the integration easier. And again, the disadvantage, if you call it that, is there will be additional parameters at which you will be integrating, but they will be a lot easier than attacking this integral directly. Okay, so it's okay if you don't understand this expression, because of course this is from quantum field theory. But what we will be doing is we will begin at a very innocent looking function 1 over a b. Okay, and of course from your basic algebra, everyone knows that you can write it, or you can expand it as 1 over a minus b multiplied by 1 over b times 1 over a. Okay, and what we do is, here's the crazy part, we write this very simple looking fraction 1 over ab, which is a product of the denominator, into an integral. Okay, so you can write this, I can write the one in the parenthesis as the integral from b to a of dz over z squared. So it should be straightforward to show that this will lead you to 1 over a times b. And again, you'll be like, oh, why are we making this simple looking expression to something like this, into something formidable? But trust me, it will make a lot things easier in quantum field theory. It's, we're talking about Feynman here. He was the one who did this Feynman parameters, and trust me when I say that it will make things easier. So basically, we have this identity, okay? And what we do is we change variables from z to x. So let x be equal to some function involving a and b, and of course z. So this is z minus b over a minus b. Of course, dx will be given by dz over a minus b. Okay, so you already have this a minus b multiplied by dz over a minus b here, so that will just become your entire dx. And then what is z squared? What happened to our z squared? So well, that is just, if you solve it from here, z is just, of course, let's just solve for z instead of z squared. Z is just, of course, let me see, x times a plus, so you have plus b, 1 minus x multiplied by b. Okay, so now our 1 over a times b in terms of the x variable now will become an integral. So now when z equals b, what is x? Obviously it is 0. When z is equal to a, what is x? So when z is equal to a, that's how x is a over b a minus b over a minus b. So this is just equal to 1, right? And z is this whole thing, so you have xa plus 1 minus xb squared, because this is z squared, and of course this entire thing, dz over a minus b, is just your dx. Okay, so now we have turned 1 over ab into an integral with respect to x. But we're not yet done. We can make it a little bit symmetric looking, the identity, by extending the integral and introducing the delta function. So we have an integration over x. Now let's do an integration over y. Okay, this time via the delta function. So our 1 minus x, let's make that y. Okay, so therefore the argument of your delta function will be x plus 1 minus y, and the denominator becomes x times a plus y times b squared. Okay, so you can show that. So when you evaluate this with respect to y, the y will be converted into 1 minus x, and then you go back here, and then when you integrate this, you get 1 over ab. Okay, so now it's a bit more complicated, but we're not yet done because this is a very simple looking identity. Note that in the Feynman one, there are 3 factors in the denominator. This is only 2. What we can do is we take the derivative of this expression on both sides. Okay, so take the derivative of this with respect to what? With respect to b. So in the left hand side, you get negative 1 over ab squared. On the right hand side, when you take the derivative with respect to b, you get a factor minus 2. Okay, and then you get a factor of y via the chain rule. So you have here a factor of minus 2. On the left hand side, you have a factor of minus 1. The negative signs will cancel. That will leave you with 1 over ab squared equals the integral from 0 to 1 of dx dy, and now delta of x y minus 1. Now you have a factor in the numerator of y, thanks to the chain rule, 2y. Okay, and of course the power here in the denominator will become cube. Okay, you can do it again. You can do the derivative again. Of course, again in the left hand side, you get a factor of negative 2. That negative 2 will cancel with this 2 here, and this will become b cubed in the denominator. In the right hand side, when you take its derivative again with respect to b, the denominator here will be raised to the 4th. You get a factor minus 3. The negative sign will cancel with the left hand side, and all told, when you take the second derivative of this one, okay, the original expression, that will give you 1 over ab cubed equals the integral from 0 to 1 of dx dy, the delta of x plus y minus 1, and then multiplied by xa plus yb to the 4th. Okay, and on the numerator, of course, you have because you will be obtaining another y when you take the derivative here. You already have a y there. This will give you 3y squared. Okay, you can do that. You can continue doing the derivative, and you can show to yourself that after taking the n minus 1 derivative, okay, so after n minus 1 differentiation, okay, after doing that, you get the following identity: 1 over a b to the n, that is equal to integral from 0 to 1 of dx dy, okay, of delta of x plus y minus 1, and then you have xa plus yb to the n minus 1, sorry, n plus 1, because, you know, second derivative, this is 4, so that's plus 2. So n minus 1 plus 2 is n plus 1. And then in the numerator, you have, so this will give you n, then y raised to the how many times you take its derivative, so n minus 1. Okay? Of course, without the delta function, I can write this as 1 over a b to the n. If you evaluate the integral over y, this will just give you an integral with respect to x of x times a plus, so y becomes 1 minus x b to the n plus 1, and then the numerator, of course, will have n, 1 minus x n minus 1. Okay? But, so that's like a times n factors of b in the denominator. But that's not what we're after, because if you notice the Feynman problem that we have in the top, you have 3 denominators. So obviously, and then they're distinct. So you need something like 1 over a plus times b times n. Okay? But we will do better than that. There's actually a general form of this expression that involves n factors in the denominator. So here you have a1 times a2 up all the way up to an in the denominator. Okay? And we will show that this expression is given by the integral. So you'll be integrating with respect to n parameters. So these are the Feynman parameters of the delta function of sum from n equals I equals 1 to n of x sub I minus 1. So that's the delta function here at the top. But now there are, like, instead of just x and y, you now have n parameters. And then this will actually generalize into x1 times a1 plus x2 times a2 and so on, all the way up to xn times an multiplied by n. Okay, and then in the numerator you have n minus 1 factorial. Okay, so now the question is, we're going to show this identity. So there are 2 ways to go about this. One is you will use the so-called Schwinger parametrization, but I'll do I think another method, which is a bit I think it will be a bit simpler, and we will prove this by induction. Okay, and to prove this by induction, of course, when you do proof by induction, you do need to have the base case. In other words, the beginning of the what do you call this, the first identity that you will need, and the base case here that we have is for n equals 2. And of course, we've already proven that identity for n equals 2, you only have 2 factors in the denominator, and this thing here in the right hand side will reduce to the one that we had above, which is this one. Okay, this is our base case for n equals 2. We have proven this to be true. Okay, so in other words, we have a base case. So now let's assume that this holds for some value of n, that this identity holds for n. That's the proof by induction. So if it holds for n, we need to show that if we assume that it holds for n, then it holds for n, the n plus 1, what do you call this, the n plus 1 case. Okay, and so to do that, we will be using this. Okay, if it holds for some n, then we need to show that it holds for n plus 1. In other words, a1 times a2 all the way up to an times n plus 1. Okay, so that is equal to, of course, a sub n plus 1 multiplied by a sub 1, a sub 2, all the way up to a sub n. Okay, so now we assume that this holds, which is the one above. We show that it holds for n plus 1. If it does, then we're done. Okay, so we substitute this, the integral form of this one, from the one from above. So that is 1 over an plus 1 integral from 0 to 1 of dx1 all the way up to dxn delta sum. So let me just, so we know that that runs for up to n. Let's just not write the labels of the summation. X sub I minus 1. And then you have x1, a1 all the way up to xn, a sub n to the n. And of course, in the numerator, you have n minus 1 factorial. Okay? So how do we proceed? So first, to simplify things so that I won't be repeating everything, let me introduce this shorthand notation. Let me call the entire denominator here, the one inside the bracket, as b. Okay? So we won't be writing x sub 1, a sub 1, that sum of the product of x and a from 1 to n. Okay? So let's do that. And so what happens is, we also put this factor inside the integration. So this will give us the integral from 0 to 1 of dx1 all the way up to dxn. And then you have the delta function sum of x sub I minus 1. Then you have 1 over a n sub 1, which is of course this one. And then you have b sub n, and then you have n minus 1 factorial. Okay? So let me rewrite this in a more nice way. Let me separate the factorial from the numerator. Still the same, but this will be suggestive, this form. So this entire thing is b, and then that is to the n. Okay. Why did I write it that way? I write it that way so that this guy, okay, 1 over a to the n plus 1 times b sub n. So just think of a to the n plus 1 as a single variable. Let's call it like, I don't know, capital C, for example, okay? So the thing is, we can use this identity that we have here, right? We can use this identity where we wrote 1 over a multiplied by b to some n as some integral, okay? And we will now use that to rewrite this guy, okay? And here our variable is called x. Let's just call our variable here as u sub n plus 1. You're like, oh, why do we call it that? Later you will see why. But we write this as the integral from 0 to 1. So our variable is du, our variable is u sub n plus 1, okay? So this guy, if you recall, is this identity. So n multiplied by 1 minus the variable to the n minus 1 over x times this guy plus 1 minus the variable multiplied by this guy without the n to the n plus 1. So this becomes, the variable is un plus 1 multiplied by a to the n plus 1, because that's our a there, okay, plus 1 minus the variable, which is of course un plus 1 multiplied by b, all of these raised to the n plus 1, okay? And of course, in the numerator, you have n multiplied by 1 minus the variable n minus 1. So it might look weird why I chose the variable n plus 1, but later on in hindsight, you'll see why, because it will generalize nicely, okay? So all in all, what happens is this whole integral now becomes integral from 0 to 1 of the x sub 1 all the way up to x sub n of the delta function minus 1. So note that you have here n minus 1 factorial, and then you multiply it by n. Of course, obviously, that becomes n factorial, right? Integral from 0 to 1 of du n plus 1 of, so let's just copy this over, un sub n plus 1 a to the n plus 1 plus 1 minus u sub n plus 1 b, all raised to n plus 1. And of course, in the numerator, note that you already included n in the n minus 1 factorial, which is n factorial. So the numerator, we only have 1 minus u to the n plus 1 to the n minus 1 left, okay? Now, let's change variables, okay? Instead of x's, we change them into u's, okay? So, in general, we let u sub I be defined as 1 minus u to the n plus 1. What is u to the n plus 1? For all intents and purposes, these i's will run from 1 to the n. And u of n plus 1 is just a number, okay, for these guys. So 1 minus some number, let's call that number u n plus 1, multiplied by xi. Of course, the xi, okay, you just take the derivative of this one both sides. So that is 1 minus u n plus 1 over, in the numerator you have dui. Of course, this is for I from 1 to n, not n plus 1, just 1 to n. So in other words, u1 up to u sub n, they are dependent on u n plus 1. Okay, that's the change of variables that we did. So most importantly, what happens to our b? Okay, notice that b we defined it by this one. Imagine if I multiplied b by 1 minus un plus 1. If I multiply b with that, what happens? Well, since b is comprised of x1 a1 plus x2 a2 and so on, if you multiply every excess by, so xi, all the xi, you multiply it by 1 over 1 minus un plus 1, they become ui's, correct? So b is x1 times a1 multiplied by this one will become u1. x2, a2 multiplied by this one will become u2, and so on. So all in all, your 1 minus u sub n plus 1 multiplied by b will become u1, a1 plus u2, a2, and so on, all the way up to un, an. Okay? So let's substitute these variables now in our original integral. So note that again, our original integral is the one we're trying to prove is the product from a1 to an sub 1. Okay? This will now become integral. Okay? Let me transfer the integral of du n plus 1 on the leftmost side. Okay? And the integral of dx from 0 to 1. But we've changed variables to u. So when x is 0, when example x1 is 0, u is 0. So the lower bound is still 0. However, when your x is 1, what is u? U is 1 minus u to the n plus 1. So you have 1 minus u to the n plus 1. So the reason why I transferred the integration of u to the n plus 1 is so that we can accommodate this variable here, which is we will be evaluating for all the ui's all the way up to n. Okay, so you have that. Your dx1 will become du1 over 1 minus n plus 1. Your dx2 will become du2 over 1 minus n plus 1, and so on. So all your dxi's will become du1, du2, all the way up to dun. Okay, and of course we have a factor of 1 minus un plus 1 in the denominator. There are n of them, so we'll write that later, but let's go back first to the delta function. So the delta function is sum from of the excess, but note that those xi's will become ui over 1 minus un plus 1. These are your xi's. So sum of xi minus 1. They now become ui's. Okay? And recall that we have n factors of 1 minus u to the n plus 1 here. Okay? From this, guys. So we write it here. 1 minus u to the n plus 1. There are n of them. And of course, we have an n factorial here originally. So you have n factorial. And then multiplied by, so in the denominator you have u1, a1, all the way up to u, let me write it below, all the way up to un plus 1, a sub n plus 1. This is raised to the n plus 1. And in the numerator, you have 1 minus u n plus 1 to the n minus 1. This is basically this one. Okay? Note that our 1 minus u to the n plus 1 bn became this guy. So now you have a sum from u1 to a1 all the way up to n plus 1. Why? Because you have a un plus 1 a plus a to the n plus 1 here. Okay? So you have that. So let's write it again. It looks so cramped in there. So this will be equal to, so of course, 1 minus u to the n plus 1 here to the n minus 1. This will cancel with this one, leaving a single factor of 1 minus u to the n minus 1. Okay? So this will be equal to integral from 0 to 1 of du n plus 1, integral from 0 to 1 minus u n plus 1, du1 all the way up to dun, delta function of the sum of u sub I over 1 minus u sub n plus 1 minus 1. You have n factorial over 1 minus un plus 1, and then you have u1, a1, all the way up to plus u sub n plus 1, a n plus 1 to the n plus 1. Again, this guy right here, okay? And then in the numerator, you have nothing anymore because we've canceled this one. So you have a 1 there. Let's look at the delta function, okay? Because that looks funny. The parameter inside the delta function is sum. And again, let's write it explicitly. This is from 1 to n of u sub I over 1 minus u sub n plus 1 minus 1. Of course, I can always expand that. I can rewrite that as, I can factor out the 1 minus u n plus 1, okay? And that gives me sum of u sub I minus, so the 1 here, I write it as 1 minus u sub n plus 1 over 1 minus u sub n plus 1. So this will become 1 plus u to the n minus 1 after factoring out 1 minus u sub n plus 1 and then multiplying by a minus sign. Okay? Of course, I can simplify that further because if you recall, the property of a delta function, when you have the Dirac delta of some function divided by something, some expression, you can always write that as that denominator outside multiplied by the delta function of the identity or the parameter inside. Okay, so we have that. So therefore, this whole thing right here, this delta function, will give us 1 minus u n plus 1, okay, multiplied by the delta function of the sum, again, from I equals 1 to n of u sub I plus u sub n plus 1 minus 1. Well, why not just include u sub n plus 1 here in the summation and then extend it up to n plus 1? Okay, so therefore, this will become 1 minus un plus 1 multiplied by the delta function of the sum, this time from I equals 1 to n plus 1, because you have included this in the summation, of u sub I minus 1. Okay, and this whole delta function, we substitute it back to the integral above. Okay, so you now have 1 over a1 all the way up to a n plus 1. That is the integral from 0 to 1 of du n plus 1, integral from 0 to 1 minus u sub n plus 1, okay, of du1 all the way up to dun. So let's look at our integral above. So this delta function will become this. So you have a factor of 1 minus u sub n plus 1 of delta of the sum from 1 to n plus 1 of ui minus 1, but you have n factorial over 1 minus u n plus 1. So of course this will cancel, and then you have this denominator right here. So you have u1 a1 all the way up to un plus 1 a n plus 1 raised to the n plus 1, and then you have 1 in the numerator. Okay, so now what happens? So this will cancel. So note this integral from 0 to 1 to the 0 to 1 minus un plus 1. But note that we have a Dirac delta inside the integrand. So what we can do is, to make it all symmetric, we can instead extend the integration. Instead of up to 1 minus u to the n plus 1, you extend it up to 1. Why? The delta function will not pick that up anyway, because it's only between 1 minus 0 to 1 minus u to the n plus 1. So if you extend it up to 1, it doesn't matter. It won't contribute to anything. Okay? So instead of 0 to 1 minus u to the n plus 1, let's extend it to 0 to 1. It won't contribute anything. So what that gives us is that now all the variables from including u to the n plus 1 will now be integrated from 0 to 1. And so we now have a very symmetric looking final identity here. Okay, you have the delta function of the sum of I equals 1 to the n plus 1 of u sub I minus 1, and then u1, a1, all the way up to un plus 1, an plus 1, n plus 1 over, under n factorial. Okay? So now, if you look at the original form, okay, so this is 1 over a1 up to an plus 1. Look at the n case. If you look at the n case, that is up to n. This is the integral of all the variables up to n. Sum of the delta function up to n minus 1 factorial, the one in the denominator is up to n raised to the n. But look here, we have here exactly the n plus 1 case, okay? The integral of the variables all the way up to n plus 1, the sum inside the delta function up to n plus 1, the n minus 1 here becomes n factorial, and the denominator will be up to u sub n plus 1 to a sub n plus 1, and then raised to the n plus 1. So in other words, we have proved the n plus case, okay? So we assumed the n case, and then we were able to show, okay, the n plus 1 case. And since we were able to show that if n is true, then the n plus 1 case for this identity still holds, then we have proved the identity via induction. Okay, so this one here, this very powerful. So let me write again the a sub 1 all the way up to a sub n plus 1 here. This is the very powerful identity that results after doing the technique of Feynman parametrization. Okay, and if you do QFT, you will be using this in evaluating the very original integral that I showed. Okay, so the three denominators will become a 1, and then you have integrals over some additional parameters. Okay, so that's it. So I hope you learned something today. It's a little bit long, but it's very important because this one I'm using this right now in doing the loop correction to the E plus, E minus to, for example, muon or hadrons, and then you do the first correction, which is the loop integral in the vertex. Okay, so I hope you understand, you learned something today, and I'll see you in the next video. All right.